Yeah. So the embedded programming part. Okay. So generally we go with how we do the programming in for embedded applications and which language we use and how to use it, how code looks like. We'll have a sample code for the embedded related programming. Okay. So we look the overview are there. Agenda of this topic is that language for the embedded programming part and preparing embedded software for your controller, how it should work, and how we will program that or download that program to controller or microprocessor, and how do we debug it. And we will look for the differentiation between C and embedded C part. How do we write a program in desktop? As we know, we did lot of program in desktop, right? So we have implemented so many program in desktop itself. Now we will move towards the embedded part, and there are some differences are there. C and embedded C we'll discuss. The first point is about embedded programming part that we may use uh, earlier days. In earlier days, there was a lot of people are using assembly programming language, which assembly programming is the machine level programming, which were used to write a program for embedded applications in assembly. So it was very difficult for a lot of people to learn this assembly, and it was quite difficulty to, understand the assembly also. And nowadays also we are using not completely. Whenever it is demand is there, we should use assembly. But the due to this disadvantage of understanding friendly user and may not be able to port to the new controller, or portability is not there. Due to its own disadvantage, we move to the high level language, which is C programming. And we have C, ADA, C++, ADA. There are a lot of other languages are used in embedded system, which are high level language. So this high level language, we convert again into the assembly. Again, assembly will convert into the executable operational code, opcode, object code, right? So that will be converted. Finally, it will given to a controller to perform the operations. So now, since we already have a basic knowledge on embedded C programming, then we can use the same C programming concept in embedded system. So we'll see how it goes in embedded C. So C, when you have a good experience in C, definitely it is a good, knowledge and weightage for exploring the embedded application. Okay, in terms of high level language. So in embedded system, we have two things. One is the host and target. Host is nothing but your computer or a personal computer where you have a complete setup for development of embedded software. Like you may need to install the cross compiler, you need to have a debuggers, everything. Okay, so that is your machine, which is host. And the word is called target. So target is the embedded software that is built by the tools, runs on the embedded system. Say we use a lot of tools to build a software. Once you build a software, when you get an output file that will run in embedded application or embedded system inside the microcontroller or processor. That is called target. Clear? So, how do we start writing a program? So basically, you need to start with first with you need to have a editor or you need to have a compiler. So generally in embedded application, we use a cross compiler. So you should have a compiler to write your program. You write your program in editing window, right? You write program, then you start saving that program into .c file, correct? So once you start saving the .c file, then the compiler will compile, then it will convert into a final executable code, correct? There are multiple processes are there in the compilation stages. So once this compilation is over, then you will get a output file. That output file you can flash it or download it to a microcontroller. So that's where it will start executing the microprocessor. Sorry, your application. So this maybe you already may know. See, when you write a program, there will be a the after saving the extension file .c, compiler will take it high level language. It will convert into low level language. And finally, there will be a object file will be created. This is given to a linker. Linker will link the library which you used from the external component, and it will link with all the multiple object file and data file together. And finally, it will relocate, assign the physical address to that memory to that executable file. Now it is converted into a perfect executable file that will be able to run it in microcontroller or microprocessor. Correct? We output of this compilation we call it as .hex file, hexa file, hex, and each these steps need to be followed to run the compile the code and get the output file. So we use a GCC or JNU tools, JNU tools. These are all cross compilers which are dedicatedly developed to get the output of the program which will run in microcontroller or microprocessor. So compiler, you know that. So it generally translates from high level language to low level. That is basically it will convert to assembly language, right? So again, it will separate out the code and data, correct? And it will check for the syntax error. If any syntax error, it will throw that. And it will give it to assembler. Assembler will convert the assembly code to object code, correct? Same data file and object file will be, the data and the code file will be, carry forwarded as it is in the format of object. So you can see, have a look here, how it works. So cross compiler, generally it will convert into the output file with respect to the assembler or with respect to the microcontroller architecture. It will convert according to the architecture of microcontroller. It will convert the object file. Okay. And data also will continue. Data is nothing but your local variable or global variable, all static variables. All part we call it as a data variable, data part. Okay. Data part and code part. So when you see the the content of the project files inside the compiler, you will get header file, code section, you will get global variable section, uninitialized global variable. It will be in the BSS section, and the symbol table will be created for your variables and functions. All it will create in this different files are there. We can have a look on that the files generation after creating a project. Okay, object file, linker file, linker file, okay, object file, and BSS section file, code file, and even the data file also will be generated. We can have a look there in cross compiler. So linker, anyway, you know that it will try to uh, gather the function definition from the library, or unknowns variable is there, it will try to find it in library. It will try to combine and create a both data and code will be a single object file will be created in linking, correct? And these are all again related to compilation stages. So linker will help us to differentiate again the which part of code and then the data should go to the different type of memory. We have it two types. One is ROM and RAM. In general, ROM will stored with code. Execution of code will be there in ROM and constant data. But variable data and global data, local data, all are stored in RAM, right? Correct? You may be aware of this. And once it is completed, then when we flash that into the memory of a microcontroller, then it will start running. But before doing that, the running or flashing, the code has to be assigned with a physical base address, because it doesn't know from where it should start and where it should store into the memory location. So that's where the locating or reloader will help us to assign the physical base address of memory location. Correct? This is the last step of compilation stages, which will get a, the program should run from the different memory location. You can see here the 8000 is the one of the memory location which your data will be stored and code will be stored here. So data will start from 8000 and your code start from 0. So 0 is the memory location. Start from 0, you store the data, and 8000 is your data code. The constant data will be stored here. Okay, it's inside the microcontroller or microprocessor. Once it's saved, then you can start running it. So how do we save it, or how do we program that controller with this our output file? So generally we use a separate programming device. We use a separate external device to program the code inside the microcontroller or microprocessor. There are separate external devices are used. The software is nothing but ISP programming part are the flash magic. The sample of the downloading softwares are flash magic or flash utility or even JTAG. These are all downloading tools, and debugging is nothing but where you need to check the code if it is working or not. Say you flash the code inside the microcontroller, a microprocessor. You started giving power supply to the controller, a processor. Now processor should start working the execution of your instructions, right? It should come inside the main function. Inside main function, it should look for the any of the local variables initialized, or any of the functions are called. Those things will be verified and it will start executing inside the while one. You know while one, right? Infinite loop or maybe your functionality. So when you call a function, it should work. If that is not working, then you need to start debugging it. Why it is not working? What is the issue? What is the options we have to debug? One is that you should use a the JTAG. JTAG is the one of the tool which will help us to debug the code in real time. Okay, I'll show you how it works one by one. Okay, that is debugging. Downloading nothing but flashing your software inside the microcontroller. Okay, that is downloading. And we have a remote debugger also, something like your controller is there in out of location where you can't access that device. At that time you need to use a remote debugging. Okay, can you see this code snippet? So I think most of the things you made we can discuss one by one. uh, the first line is that hash include. I hope you are aware of the hash include, right? So what is the use of hash include? Yeah. In general, this hash include will help us to, include the library functions. Our library particular, things can be added to a program. So here reg 1657 is the one of the header file which has the controller specific informations. So nothing but you may know that registers. You remember that predefined variables in VLSI is called registers, like P0, P1, P2, Tcon, T0. You remember that we discussed in microcontroller? Tcon, Scon, Tmode, and P0, P1. These are all the port registers, and control registers are like Tcon, Scon, serial control register, timer control register, Tmode, timer mode register. These are all the registers which are available in this header file. Okay, this is available in header file. those header file will be included here. Why we want to include? Because we want to use those registers. You can see in this the line number, I can't say line, there is a P2 R is equal to 0 cross 0 1 semicolon. P2 is the one of the predefined register, that is register. So respect to a microcontroller, we have a register. You can use P0 also, we can use P1, P2, P3 also. So this is the one of the register which is available in this header file. reg167.h is a header file. It is header file for a specific application, okay, or specific microcontroller. For each specific microcontroller, we will have a header file. This will be readily available in the compiler. No need to worry. It will be there in your compiler. You can just include, you can start using it. Okay. And the next line, void, white and void, and flower bucket open, flower bucket close. What is this? Void, wait, void, and flower bucket open and close. What is this looks like? Yes, correct. Definition. It's a function definition which doesn't have any arguments to pass and doesn't return any data, and it doesn't have any statement also. It's a kind of dummy function. Dummy or empty function. Why we are using, we'll get to know later. Okay, we'll discuss. We'll go to the next line. Next line is void main. Yeah, void main void. This is the main function for each of the embedded application. This should be there. Otherwise, it won't work. So inside the main function, we have a unsigned int I. What is this? Hmm, okay. Hmm. So here we have declared a variable, correct? The variable name is I. It is a local variable to this function, main function. It's a local variable to a main function. So the next line you can see while one. So one is the number, or it's a kind of Boolean data which is true, always a true. The condition remains same forever. So while one is the infinite loop, inside that we have a some in statements. We can go through one by one. So statement P2 is equal to R is equal to, this is a R operation which is doing R operation with the data 0 cross 0 1. So it is trying to switch on the LED of the P2 dot 0 pin, that is they are making 1. Just we are trying to toggle or switch on the port pin, correct? This is what the hardware programming part. Generally, this is looks like we are trying to write a program for the microcontroller hardware. Okay, so that's why embedded C we call it as a hardware oriented programming language. And for I is equal to 0 and I is less than 10,000, I plus plus and wait. Wait is the one of the dummy function. So they are calling this function around 10,000 times. So why they are calling this 10,000 means they are trying to waste their time. Waste the CPU time, not our time, CPU time. CPU should waste time here to get to know this port. P2 should be when it becomes 1, that should be it should be able to visible to the user, because controller runs very high speed. It will be in a very high speed, something like per second or per microsecond. 1.85 microsecond means that is one of the frequency, the clock time of a instruction execution time of a microcontroller. Okay, which it takes in terms of microsecond it will take. So if that is the speed of microcontroller, we will not be able to see physically this port is on or off, the LED is on or off. To see that LED or see that the light is glowing or not, we need to have a delay between them, between the on and off time. If delay is there, we'll get to know, oh yes, it is on or it is off, like that. To create that such kind of delay, they have called this for loop and they call this dummy function. It will spend at least little bit time there where we can able to see the high, and the next line we have a low, configuring the low. P2 on is equal to negation of 0 cross 1. Negation of 0 cross 1 is nothing but FE you will get. 0 cross FE. Negation is a one of the operating operator which you use in bitwise operator. Whatever it, if you give 0, it will convert into 1. If you give 1, it will convert into 0. If you see this 8-bit data 001, 01, this if you convert into negative, the 1 byte of data will be FF. If you convert FF to 0, you will get 00. Now 01 if you convert, you will get a FE. FE. If you want to see, you can check in your from your side, write down the convert this into binary, and you can convert the high to low. Okay, this is the output of FE, means last bit they are going to make it 0. If I make it 0, then it will become a off state. Off state. Off state. That off state will be a on off or on off, like. So after that off state, there should be again delay should be there. If you don't give delay, you will not be able to see in the physically does it really working or not. Okay, so that's why we use the another for loop for providing a dummy delay. Just delay, make it delay. On off. If I tell in a speed also on off on off on off, but even I can tell on off on off. This is the one of the reason where we should use a for loop to delay the time to see the output in the hardware. Because if it is goes fast, we will not be able to recognize either really it is on or off. Okay, this will continues, keep on continues till the power is there in microcontroller. That's why it is in while one, infinite loop. Correct. So after coming out of infinite loop, it will be there in main one. Are you getting this program which works just toggling of the LED in a controller? This is a basic microcontroller programming concept. This we can simulate and check it in our Keel software. We can see that. Hmm? So you can see explanation is there for each of the line. This is include which we included the library. This is a dummy function which we just defined to call this as a dummy function, and we should have a main function to run the all embedded application, and inside that we are declaring a 2-byte integer data variable, integer variable. We use that variable to perform the operation, and these are all the files will be created after creating a project in the macroversion. I'll show you how to create a Keel software project in Keel software. Okay, and the once you create, you will get a multiple files creation. One is that list subset, object file, again the object, and again linker file, and then final executable file .hex. This will be generated. Okay, I'll show you all these files in program. Yeah, this is the one of the example for embedded application, and we have a Keel software which you need to install and run it. You can use the C51 exe file to install the your application tool. Okay, you might have done it. If you are not done, we can do it. And the compilation stages you can see one by one how it works here. We should have a prototype of wait function because this is used in inside the main function. It is defined below the main function. That's why we should have always the prototype. Correct. and remain things you can study yourself. And this is looks like the assembly programming concept. As you know that cross compiler will convert into assembly based on the architecture defined in in compiler. If you select different architecture, it will generate different source code. Okay, this is looks like assembly code. You may not understand. We can continue further. Yeah, coming to the embedded and desktop oriented, as you got very lavish and luxurious memory allocation in desktop, but same thing cannot be done in embedded system because it will have very limited memory, very less. So within that memory, we should have write our programming concept and data variables. Okay, the major challenging part in embedded system is that you should write a optimized code. You should not write a very large code. It should be optimized and clear and neat code. Okay, and that's why we call it as well, since we access the GPU port input output ports from microcontroller, we call it as a hardware oriented programming language. Hardware oriented programming language. Even embedded C also will have a special keywords called timer, interrupt, ISR. These are all used because this will help us to write a program for interact with external device. Okay, and even GPU port is also has the actions to connect to the external device. That is also a external communication part. That's why again we can call it as a hardware oriented programming language. And it has a special keyword is called ISR and interrupt. You know, right? Interrupt. Yeah, this is about the difference between C and embedded C memory part. Yeah, earlier days assembly was there. During assembly, they used to have this go-to statement, but nowadays we don't see because may not be needed for any application. If needed, it will be handled in a microcontroller itself. No need to worry. Go-to statement is not important, but you can use it. And global variable, already we know that whenever we need, we can install it. Right? Global variable. If they all people has to be accessed, then you should have a global variable. Right? If some register want to have only the control over the enable disable, then that is also possible. You can also do that. These are all the activity which you need to perform once you get a coding part. It's not mandatory, but you should have it. And summary in the embedded programming concept, as you know that we should learn about C language concepts so that we can carry forward same thing in the embedded system, right? And again we have a different compilation stages in embedded C and even C also. Both are same, but little bit difference is there. Okay, and cross compilers are used to compile the code for microcontroller. Correct. Cross compiler, like example is Keel compiler. And do you know the linker and relocator? What happens? Generally, it will link the all library functions together, and linker will assign the physical base address to memory to start running. Okay, clear. This is all about the C language and embedded programming part. How do we program? What is the language we select? Correct? Mhm. Which one is the best language for a particular controller? You can decide. So in general, most of people we use a C programming. Okay. Any other questions you have?